Hello and welcome to this presentation on trigonometric equations. It's assumed that you've seen the presentation on trigonometric identities before commencing this work. Equations containing trigonometric ratios are termed trigonometric equations. Generally, there are an infinite number of solutions to these types of equations, but we restrict our solutions to the values of between 0 and 360 degrees or 0 and 2 pi radians. An understanding of the angles of any magnitude is essential in the solution of these types of equations. Not all calculators will provide all possible solutions, so we need to be aware of what the solutions might be. To do this, we're going to use an Astc diagram, which is shown over leaf, and that provides a summary for the angles of magnitude between 0 and 360 degrees or 0 and 2 pi radians. This plot shows the sine and cosine waveforms. We plotted between 0 and 360 degrees. That's one complete cycle of the sine and cosine waveform. Don't forget these are periodic, continuous waveforms. They go on forever. So there's an infinite number of solutions to all the problems we're going to look at. But we're just going to focus on 0 to 360. The waveform has been split into quadrants. There's a 0 to 90 quadrant here. There's a 90 degree to 180 degree quadrant here, second quadrant. There's a 180 to 270 degree quadrant across here, third quadrant, and there's a 270 to 360 degree quadrant across here, that's the fourth quadrant. So we've got four quadrants that we're splitting the curve into. What you notice in the first quadrant for the sine and cosine waveform is that they are both positive values of the ratio. They are above the x-axis, if you like. When we go into the second quadrant, the sine waveform is still positive in this quadrant, but the cosine waveform has now become a negative value in this quadrant, or the ratios are negative. When we go into the third quadrant, the 180 to 270 degree quadrant, we find that the sine value now is negative. All the sine ratios here are negative values, and all the cosine ratios are also negative values. When we go into the fourth quadrant, the final quadrant, we find that the cos ratios are now positive, but the sine ratios remain negative. And those characteristics we're interested in. Here's a plot of the cosecant, which don't forget is 1 upon the sine curve, and the secant curve, which is 1 upon the cos curve. Now don't worry too much about the shapes here, we're not really worried about the actual shapes of these curves, but we're interested in their ratios. Are they positive and negative in the various quadrants? And if you look at them again, you'll see that in the first quadrant, 0 to 90 degrees, they're both positive ratios. Both the cosecant and the secant curves are positive. In the second quadrant, the 90 degrees to 180 degrees quadrant, you can see that the cosecant curve, which is the 1 upon sine curve, is positive, and the secant curve has negative ratios. When we go to the 180 to 70 degree quadrant here, we see that both curves are now in the negative ratio region. In the last quadrant, the 270 to 360 degree quadrant, we see that the secant curve, the 1 upon cos, is now positive, whilst the cosecant curve, the 1 upon sine, is negative. When you compare these curves to the previous curves of the sine and cosine curves, you notice they have very similar characteristics. In the same quadrants, they have the same ratios, values, positive or negative. On this plot, we have the tangent curve and the cotangent curve. Don't forget the cotangent curve is 1 upon the tan curve. Again, we plotted in our four quadrants here, 0 to 360. Taking the first quadrant, 0 to 90 degrees, we can see that the tangent curve has positive ratios. It goes off to positive infinity, and the cotangent curve is also positive. In the 90 to 180 degree quadrant, the second quadrant, both of the curves are negative. In the 180 to 270 degree quadrant, both of the curves are now positive, and in the 270 to 360 degree quadrant, both of the curves are now negative. So summarizing the previous curves, we can construct an Astc diagram. The A stands for all, the S stands for sine, the T stands for tangent, and the cos stands for cosine. In my day, when I was at school, they used to call this the All Saints tennis court as a way of remembering, a mnemonic kind of way of remembering the Astc diagram. Some people have called it all schools teach chemistry. It doesn't matter how you remember it. It's just an Astc diagram. And I'll show you what the Astc means in relation to the previous plots, which I've shown on the left-hand side for convenience here. What it's trying to tell us, if we start from 0 degrees here and we go in a anti-clockwise direction, then 0 to 90 degrees in this quadrant, all the ratios, the sine, the cos, the tan, the cosec, the sec and the cot are all positive. And you can see that on the diagram on the left-hand side here, that all the curves here on the diagrams that I've plotted previously on the previous page, just shown for convenience here, they're all in the positive sector of the diagram. They all got positive ratios, in other words. So in the first quadrant, 0 to 90 degrees or 0 to pi upon 2 radians, we've got all ratios positive for all curves. When we go into the second quadrant, what we notice now is only the sine and the reciprocal of the sine, the cosec curves, are now positive. And again, you can see that from these curves on the left. For the sine curve there, we've got a positive ratio values, and for the cosecant curve, we've got positive values. For every other curve, they're always negative in the second quadrant. If we go to the third quadrant, which is the 180 to 270 degrees quadrant, or the pi to 1.5 pi, 3 pi upon 2 quadrant, what we notice now is that only the tan and its reciprocal, the cotangent curve, are positive. And again, you can see this on the curves below. If we look at the tangent curve and we look at the cotangent curve, they are now positive ratios, where all other curves you can see above are in the negative sector. And now looking in the last quadrant between the 270 and 360 degrees sector here, or the 3 pi upon 2 radians in 2 pi radians, we now find that the cos and the secant curve, which is the reciprocal of the cos, is positive and all other curves are negative. And once again, you can see this from the diagram. In the last quadrant, there's the cosine curve, and that's positive, and there's the secant curve, and that's positive. All other curves are now negative in the last quadrant. You'll see in the questions that follow how useful this diagram can be to find all the possible solutions to a particular problem. So we're going to keep referring to the Astc diagram in all the work we're going to do. This slide is just for backdrop, and it relates to the angular units of measure. Decimal notation, don't forget, is always in terms of degree, and we're probably very familiar with decimal notation. There is also what's called sexagesimal notation. This is called the degrees, minutes and seconds notation. So this is used in some of the questions. Don't forget, in terms of degrees, there are 360 degrees in a circle. In terms of minutes, if we're in sexagesimal notation, there are 60 minutes in a degree. And we know, that's by 60 with a little dash. And as far as seconds are concerned, there are 60 seconds in a minute, so 60 double dash. Okay, so we can do conversions between decimal degrees and sexagesimal notation. I do not want to get into that in any great way in this particular presentation. I've shown below in example 1 how to do this manually, but we would always do this on a calculator where we need to. The next slide shows you how to do this on a calculator. Okay, just for reference then, if we wanted to convert angles from decimal degrees into degrees, minutes and seconds, there's a button on our calculator. It looks like this on most calculators for degrees, minutes and seconds. Some calculators actually have DMS written on the button instead of the symbols there, but it means the same thing. So for example, go straight to an illustration here. If I wanted to calculate 37.6 degrees in terms of degrees, minutes and seconds, all I do is type 37.6 on my calculator, I press equals, and then I press the DMS button, and I get the value of 37 degrees and 36 minutes. So I've gone from decimal degrees into sexagesimal notation. If I want to reverse the process, I want to go from 37 degrees, 36 minutes into decimal degrees. This is the way I do it on the calculator. I type in 37, and then I press my DMS button, so the calculator knows that's 37 degrees. I then type in 36 and press the DMS button, the calculator knows that's minutes. If I had seconds, I would then type the seconds in and press the button again. In this case, I don't, so I press equals, that puts into the calculator's memory, and if you press then DMS button one more time, you get the 37.6 degrees. So what you're seeing there is the extent of the knowledge you need to understand how to do the conversions in the solution we're going to look at, where they occur. Okay, we're going to look at the forms of equation we're going to now solve. I've stated here a generic expression of a multiplied by the sine squared of x plus b multiplied by the sine of x plus c is equal to 0. That's a generic form, but you'll see in a moment there are 4 types of problem we need to solve, and so there are 4 types of solution we need to be aware of. So type 1, this is a situation where the a is equal to 0. In other words, the first term in the above generic equation disappears. So we end up with b multiplied by the sine of x plus c is equal to 0. Type 1 solutions are a direct rearrangement to solve. So simply taking c from both sides and dividing by little b, we get sine of x is equal to minus c upon b. To find the value of x, we need to take the inverse sign, or the arc sign that's sometimes used to find the value of x. So x is equal to sine to the minus 1, the inverse sign, of minus c upon b. There will be 2 solutions to this type of problem in every case. We only specify answers between 0 and 360 degrees, of course. The ratios of the minus c upon b, the value of minus c upon b, must be between minus 1 and plus 1 to find an actual solution. So values that are greater than that, which sometimes can occur, have no solution. Type 2 solutions, this is where the b term is 0. So in other words, in our generic expression, this term here disappears completely. So we end up with an equation of the form a times the sine squared of x plus c is equal to 0. Again, as for type 1, this is a direct rearrangement to solve. We simply take c from both sides and this time divide by a, so we get sine squared x is equal to minus c divided by a. If we square root both sides, we then get sine of x is equal to the square root of minus c upon a. Don't forget the c and a are actual numerical values. To find the value of x, we take the inverse sign of both sides, so we get sine to the minus 1 of the square root of minus c upon a. Now don't forget, when you take a square root, there are always 2 solutions. So in this particular case, we will end up with a plus and minus value for x. And that will actually result in a positive and negative values, giving us 4 values of the solution. There will be actually 4 values for x. There will be 2 values of x relating to the plus ratio and 2 values of x relating to the negative ratio. You'll see this on the examples over the page. Again, our ratios must be between minus 1 and plus 1 to have any real meaning to the problem. So any values of ratios greater than the plus 1 or the minus 1 cannot be solved. Okay, type 3 equation, this is where the entire equation shown above has to be solved. So we have to solve an equation to the form a times sine squared x plus b times sine x plus c equals to 0. So in this case, our a, our b and our c do not equal to 0. So this kind of equation, the a times the sine squared x plus b times sine x plus c is equal to 0, is a quadratic equation in terms of sine x. We can solve this in 2 ways, with factorization, if it will factorize, or using the quadratic formula. So if we're using the quadratic formula, don't forget we are solving for sine of x, not x, but the sine of x. We'll have to take the inverse sign to find the values of x. And the standard quadratic equation applies, minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. In some questions there will be 4 solutions here, and in some questions there will be 2 solutions. And the final type of equation is going to end up in the form shown above, but first of all we will have to use a trigonometric identity to get it into that format. Don't forget, from our previous presentation we looked at trig identities, such as cos squared x plus sine squared x equals to 1 is a trig ID, 1 plus tan squared x equals to sec squared x, another trig ID, cot squared x plus 1 equals to cosec squared x is another trig ID. So with a type 4 equation, we'll have to insert a trig ID, an appropriate trig ID, to get the equation into the format of the a sine squared x plus b sine x plus c equals 0. And of course, don't forget that could be an a cos squared x plus b cos x plus c is equal to 0, or an a cosec squared x plus b cosec x plus c is equal to 0. It could be of that format. You'll see in the examples that follow the sort of formats of the equation. Okay, we're now going to solve some trigonometric equations. I'm going to start with type 1 equations. Example 1a. We're asked to solve the trigonometric equation 5 multiplied by sine of theta plus 3 is equal to 0. We need to find all the values of theta between 0 and 360 degrees. So as this is a type 1 problem, we can simply rearrange the equation to find theta. So in this case, taking 3 from both sides, dividing both sides of the equation by 5, and then taking the inverse sine to the minus 1, we can find the value of theta. So in this case, sine to the minus 1 of minus 3 divided by 5 is minus 0.6. What we need to notice here is that this is a negative ratio. So for a sine waveform, a negative ratio occurs in the third and the fourth quadrant of our Astc diagram. So in this case, taking the inverse sine of minus 0.6 will give us a value of minus 36.87 degrees. Now I've called that angle beta because although this is a solution for theta, which is what we're trying to solve for, this is not a solution that we're allowed to give because our solutions must be within 0 to 360 degrees, and this is outside that range. So it is a solution for theta, but not one we can actually specify in this question. So now what I'm going to do is use the Astc diagram to find values of theta within the range of 0 to 360. So you can see on the Astc diagram, I've labelled angle beta here, this angle in here, and angle beta over here, angle there. Now this is the third and the fourth quadrant of the Astc diagram where the sine waveform has a negative ratio, and don't forget we've got minus 0.6 as our ratio here. So if I replace the beta with the angle of 36.87, I can work out a solution for theta. One solution is going to be 180 degrees plus the 36.87, which will give me 216.87 degrees. So that's a solution for theta. And the next solution I've got here is 360, take away the beta angle here of 36.87 to give me 323.13 degrees. So now what I've done using the Astc diagram is find my two solutions of theta within the 0 to 360 degree envelope. The next slide shows in more detail how to actually calculate these particular values of theta. Okay, example 1a continued here shows us how we obtain our two solutions. So from the Astc diagram, we know that one solution for theta is 360 degrees take away 36.87. So one solution is 323.13 degrees. So on our diagram here for a negative 0.6 ratio, doing our inverse function here, we end up with a value of 323.13 degrees for theta. Okay. And then also to get the second value of theta, we know from our Astc diagram it's 180 degrees plus 36.87 degrees. So 216.87 degrees is our second solution. So again, this minus 0.6 ratio, this line here cuts the curve here and gives us the 216.87 degree value. So our two solutions here are in the third and fourth quadrants, and we can find that from the Astc diagram. I suggest you just recap that for yourself and understand how we end up with those two values of theta in the third and fourth quadrants. Again, try and go back to your Astc diagram. That might help you with your understanding. So question 1a here, I've asked to solve the equation 1.5 times the tan of a, take away 1.8 is equal to 0. Got to solve it between 0 degrees and 360 degrees as usual. There'll be two solutions. So given the equation in the question, I can simply rearrange the equation to find the value of a. So adding 1.8 to both sides, dividing both sides by 1.5, taking the inverse tan, the tan to the minus 1, I can find the value of what I call alpha. So in this case, putting the numbers in, that's tan to the minus 1 of 1.2. Now again, thinking of our Astc diagram here, tangent occurs positive in the first quadrant and in the third quadrant. So the first value of a I'm going to get here is the value given above. I will get tan to the minus 1 of the 1.2 gives me 50.19 degrees. That's my first value of a. Thinking to my Astc diagram, in the third quadrant I will find a positive value, a positive ratio for tan. So I will get an A of 180 plus 50.19 degrees. So I get 230.19 degrees as my second solution. Question 1a continued here. So angle A from the previous slide, first angle was 50.19 degrees, and angle A was also shown to be 230.19 degrees for our two solutions. Looking at the Astc diagram, you can see that the first angle for a positive ratio of 1.2 would be here. So 50.2 is in that first quadrant where all the ratios have positive values. And the tangent also occurs as positive in the third quadrant. So that 50.2 degrees angle I can write in here, this angle here. So that will be then 180 plus the 50.2 degrees to get the value of the second location for the answer there. So if you look at the actual tan curve here, the ratio's on the worst vertical axis, and my y is equal to tan x function here. Again, you can see for a positive ratio of 1.2, it hits the curve, tan curve here, which gives you the 50.2 degrees in the first quadrant, and that 1.2 line projected across horizontally hits the tangent curve here, and that would be the 230.2 degree solution also. Again, I encourage you to take a moment to look at that and understand how we end up with our two solutions. Okay, type 2 solutions. Here, example 1b is a type 2 problem. We're given 2 take away 4 multiplied by the cos squared x is equal to 0. We've got to find the values of x's between 0 degrees and 360 degrees. So again, this is the rearrangement, a type 2 problem. We can rearrange it to find our solution, but there will be 4 solutions in this particular problem. So given 2 take away 4 cos squared x is equal to 0, I can simply rearrange the equation. So I can first of all add the 4 cos squared x to both sides to make it positive. I've written it on the left hand side here. So 4 cos squared x is equal to the positive 2. I can divide both sides by 4, so cos squared x is equal to 2 divided by 4, and then I can square root both sides. So cos x is equal to the square root of 2 divided by 4 is a half, of course, the square root of 0.5. Now don't forget, when you take a square root, you get a plus and a minus answer. There are always 2 solutions. So the square root of 0.5 is 0.7071, 4 decimal places. So in other words here, to find the value of x, I take the inverse cos, or the cos to the minus 1 of the plus or minus 0.7071, and I will get from my calculator plus or minus 45 degrees. So my 2 solutions of plus 45 degrees and minus 45 degrees. Now again, going back to our Astc diagram, don't forget the quadrants in which the cosine function is positive. The first quadrant, all functions are positive in the first quadrant, and the fourth quadrant, only the cos function is positive in the fourth quadrant. So on the next slide, we'll see how we use that information. Okay, example 1b continued here. So from the previous slide, we know that we get plus or minus 45 degrees for our solution. So we've got 4 solutions here. Taking the plus 45 degrees, we know that in the first quadrant, all the ratios are positive. So for our cos function here, we definitely got a solution in the first quadrant. It's plus 45 degrees. We know that in the fourth quadrant, for our cosine function, we get a positive ratio value, so we've definitely got a solution in the fourth quadrant. That will be 360 degrees take away 45 degrees. So that's how I get the 315 degrees. So from the plus 45, I've got my 2 solutions. Plus 45 is a solution, and then knowing that the cosine curve is positive in that final quadrant, I know that 360 take away the 45, 315 degrees is another solution. But we also have a negative ratio value, and that gave us a negative 45, and we know that in the second quadrant cosine is negative. So here, to get my solution, I would take 45 from 180 degrees, so that will give me 135 degrees another solution. And I also get a negative ratio in the third quadrant where I would add now 45 degrees to 180 to get the 225 degrees. So that's how I arrive at my 4 solutions here, because I've got a plus and a minus 45 degrees from my equation, and I know that their plus ratio and a negative ratio will give me two values. If you look at the actual cosine curve that's plotted for us here, the ratios on the vertical axis, then you can see for a positive 0.7071 ratio, if I draw a horizontal line, it cuts the curve here, which is where I get my 45 degrees, and it cuts the curve in that fourth quadrant there here, and that's where I get my 315 degrees. If you look at the negative ratio for the curve, negative 0.7071 here, that gave me the minus 45 degree value. Then again, plotting a horizontal line across, it cuts the curve here, that gives me the 135 result, and if I continue the horizontal line across, it cuts the curve here, and that gives me the 225 solution as well. So again, I encourage you to have a look at that and see if you understand how we derived all four solutions there. Question 1b here. We're given that 1.3 is equal to a half multiplied by cot squared x. Got to find the value of x between 0 and 360 degrees. So given the equation, half times cot squared x is equal to 1.3. I'm going to rearrange to find the value of x. So first line, I'm going to multiply both sides throughout by 2 to get rid of the half on the left hand side. So cot squared x is equal to 2 times 1.3 is 2.6. On the next line, I've square rooted both sides, so on the left hand side, cot x is now equal to the square root of 2.6. Don't forget, when we take a square root, we get two answers, so in this case we get plus or minus the 1.6125, square root of 2.6. Now noting that cot x is equal to 1 divided by tan x, in other words they're reciprocal of each other, I can replace the cot x on the left hand side on the next line with tan x. In other words, I've turned that side upside down, which means I must on the right hand side turn that upside down. So instead of having 1.6125, I have 1 divided by 1.6125. In other words, I've turned it upside down. So by doing this, I can then solve this in terms of tan and not cot. So just think that step through for yourself, the way you've turned the left hand upside down and then the right hand side of the equation upside down. We're using the reciprocal relationship of cot x is equal to 1 divided by tan x. On the next line, tan x is simply equal to the 1 divided by 1.6125, which is 0.6202. Don't forget we still got the plus or minus solutions. So in this case, we've got a tan function. So tan is positive in quadrants 1 and 3 on our Astc diagram, and it's negative in quadrants 2 and 4. And we need to be aware of that as we progress the solution. Question 1b continued here, just repeated the value of tan x there. It's plus or minus 0.6202. So taking the inverse tan now, we will get an x is equal to 31.81 degrees, and that's a solution because in the first quadrant all functions are positive, so 31.8 will be a solution for the first quadrant. We know also that tan is positive in the third quadrant down in here on our Astc diagram. So if we add 31.8 degrees to 180, we will get the next solution. So that's where the 211.81 degrees comes from. And then we know when we get a solution of negative 31.81, because we've got a plus or minus, don't forget 0.6202, so this will give us a negative 31.81 degrees when you take your inverse tan. So negative ratios occur in the second quadrant for the tan function, so we will get 180 take away the 31.18, so that will give us the 148.19 solution, and then also it's negative in the fourth quadrant here, so the tangent function is negative here, so we will get 360 take away the 31.18, so that will give us the final solution of 328.19 degrees. So our solutions to this problem, there are 4 of them. X is equal to 31.81 degrees, or 148.19 degrees, or 211.81 degrees, or 328.19 degrees. The 4 solutions here because we've got a plus or minus ratio. Question 1b continued here, just a plot of the tangent curve. So for the ratio of positive 0.6202, which would be this sort of value somewhere up here, we would get two solutions of here of the 31.8, and we would also get a solution up here of the 211.8 degrees. And then for the negative ratio of the minus 0.602, will be somewhere down there. If you follow that line across, you'll get a solution here, which will be the 148.2 degrees, and following line across to here, we will get a solution of 328.2 degrees. Example 1c. This is now a type 3 problem. This will end up with a quadratic type equation. We're given 8 times the sine squared t plus 2 times sine of t is equal to 1. Got to find all the values of t between 0 and 360 as usual. So this function 8 times sine squared t plus 2 sine t minus 1 equals 0 is a quadratic equation in terms of sine of t. Now we can solve this one two ways. It can be solved with factorization, which I've shown here, or you could solve it with the quadratic equation, which I'll let you do if you want to use that. So factorizing two brackets, I get 4 times the sine of t minus 1 in one bracket, and then 2 times the sine of t plus 1 in another bracket. If you expand the brackets, you'll get back to the 8 sine squared t plus 2 sine t minus 1 is 0. To solve for the roots of the equation, our solution, I equate each of the brackets to 0 when I'm factorizing. So 4 times the sine of t minus 1 is equal to 0. Rearranging to find the sine of t, that's going to be add 1 to both sides, divide by 4, gives me the 1 upon 4, 0.25. Second solution, I've got 2 times the sine of t plus 1 equals to 0. So here you take 1 from both sides and then divide both sides by 2. So sine of t is equal to minus half, or minus 0.5. When I take the inverse functions for t to find t, so sine to the minus 1 in this case of the first root of 0.25, that gives me a value of 14.48 degrees. Now don't forget a positive ratio, positive 0.25 for sine occurs in the first and the second quadrants here. Okay, so my first solution is the 14.5 degrees in the first quadrant. That's a valid solution. But in the second quadrant, it will be 14.5 take away from 180 degrees. So to find my second solution, I will get 165.82, 180 take away the 14.5 degrees, rounded up there. And then don't forget with the negative ratio, we've got a negative 0.5 ratio, taking the sine to the minus 1 of the minus 0.5 will give you minus 30 degrees, and the sine function is negative in the quadrants 3 and 4, these quadrants here. So I will get 180 plus 30 degrees will be another solution of t, so 210 degrees, and I will get 360 degrees take away 30 degrees, get the final solution of t, 330 degrees. Right? So there are my 4 solutions, again 2 associated with the positive value ratio, the positive 0.2 ratio value, and 2 noted with the minus 0.5 ratio, the minus 30 degree value. Question 1c here, this is a type 3 solution again. That is in terms of the cos function. I've got 6 times cos squared of alpha plus 5 times cos of alpha is equal to 6. I've got to solve for alpha between 0 and 360 degrees. So given the equation, it's a quadratic equation in cos alpha. Again, I've shown it can be solved with factorization or the equation here. If you're solving it with factorization, you'll get 2 brackets of 3 times cos alpha take away 2. In one bracket multiplied by 2 times cos alpha plus 3, and that equals to 0. And you can solve that through to find that cos alpha is equal to a positive 0.6 recurring ratio, or cos alpha is equal to minus 1.5 ratio. If you want to do that with the quadratic formula, I've shown a solution here for those of you that want to use the formula. Just be careful when you pick up your values for A, B and C, you get the correct sign associated with them, but you get exactly the same answers for the cos alpha. Again, you get the 0.66 recurring at 2/3 there, or you get the minus 1.5. Now you'll see in a moment the minus 1.5 is not a valid solution because it's greater than the minimum value on a cos curve. Question 1c continued here. So to find the value of alpha, I take the inverse cos, I've labelled it as arc cos here, that's cos to the minus 1, of 0.66 recurring here. That gives me 48.19 degrees, which would be a valid solution because in the first quadrant all the ratios are positive, so I will get a positive value of alpha of 48.19. And don't forget, the only other location where a positive ratio occurs for the cosine function is in the fourth quadrant here. So my second solution for the 0.66 ratio will be 360 degrees take away the 48.19, so the second value of alpha related to the ratio of 0.66 recurring is the 311.81. Now notice the second root I found on the previous slide was minus 1.5, and that has to be ignored in this case. There is no solution for a negative 1.5 ratio because the curve only goes down to minus 1, so the negative 1.5 is off the curve and it makes no sense mathematically. So we ignore that second solution in this case. So our values of alpha are simply going to be 48.19 degrees and the 311.81 degrees. Question 1c continue, just showing a plot of the cosine wave function here, and again for the 0.66 ratio you can see where the two solutions occur. We project the 0.66 recurring ratio across, we get these two solutions here. Alright, there are no negative solutions because minus 1.5 is off the curve. Okay, type 4 solutions, the final type of solution we need to look at here. Example 1d is a type 4 solution. We're given 5 times the cos squared x plus 3 times the sine of x is equal to 3. Going to find our solutions of x between 0 and 360 degrees again. Now, this is a case where in our equation I've got two functions. I've got a cos function and I've got a sine function. So I have to try and remove one function to leave it in terms of either cos or sine. Now, given that 5 times cos squared x plus 3 sine x minus 3 is equal to 0, the trick here is to go back to our trig identities, and I'm looking here at the cos squared x plus sine squared x equals to 1 identity that we've used in previous work. And what I'm going to do is rearrange it in terms of the cos squared term here. So I'm going to rearrange it so that cos squared x is equal to 1 minus the sine squared x. If I now put that in for the cos squared x function in my original equation, I get 5 times, not cos squared x, but 1 minus sine squared x, plus my 3 sine x minus 3 is equal to 0. Now by substituting in for the cos squared x, what I'm going to do is basically eliminate it from the equation, and I'll end up with a function in terms of sine squared x and sine x, and that will be a quadratic in sine x. Just looking at the rearrangement here, expanding the bracket on the next line, I get 5 times 1 is 5. Take away 5 times minus sine squared x, so that's minus 5 sine squared x, plus my 3 sine x minus 3 is equal to 0. And then bringing the numerical values together, 5 take away 3 is 2. So on the next line I get minus 5 sine squared x plus 3 sine x plus 2 is equal to 0. And all I've done on the next line is just to simplify the numbers for myself when I come to use the quadratic solution over the page. I'd simply multiply throughout by minus 1 here, just to change the sign. So the minus 5 now becomes a plus 5 times the sine squared x, the plus 3 becomes a minus 3 times the sine x, and the plus 2 becomes a minus 2 is equal to 0. So I've got a quadratic in the sine of x. Example 1d continued. I factorise this equation. If you want to use a quadratic formula, that's fine, but I'm showing factorisation here. So 5 times the sine of x plus 2 in a bracket multiplied by sine of x minus 1 is equal to 0 here. So again, going through the solution of solving this, equate each of the brackets individually to 0 to solve. So 5 times sine of x plus 2 is equal to 0. Rearranging, I get minus 2 divided by 5 is equal to minus 0.4. So the sine of x of minus 0.4 is my first solution I'll be looking for, and then taking the sine x minus 1 equals to 0, that results in sine x is equal to 1 here. So looking at the solutions, sine to the minus 1 or arc sine of the 1 ratio will give me 90 degrees, so x is 90 degrees, so on my curve there for the ratio of 1 I get a value of 90 degrees. And taking sine to the minus 1 of minus 0.4, the negative ratio, I get minus 23.58 degrees. So a negative ratio, don't forget that will put me in quadrants of 3 and 4 for the sine curve. So in quadrant 4, that will be x is 360, take away the 23.58 degrees, so 336.42 degrees will be a solution. And I'm in the third quadrant, so that will be x is equal to 180 plus the 23.58 degrees, so a solution is 203.58 degrees. So for a negative 0.4 ratio, following that line across, it cuts the curve here, relates to 203.6, and it cuts the curve here, relates to the 336.4 degrees. Okay, question 1D here is a type 4 problem. We're given 18 times the sec squared of A is equal to 21 plus 3 times the tan of A. Got to find the values of A between 0 degrees and 360 degrees. So the first thing I'm going to do is rearrange the equation and get all the terms onto one side of the equation so it equals to 0. So I'm going to take 21 from both sides, and I'm going to take 3 times the tan of A from both sides. So rearranging, I get 18 sec squared A, take away 3 times the tan of A, take away 21 is equal to 0. I notice in this particular question I can divide throughout by 3 and simplify my numerical values. That doesn't always occur, but it does in this question. So dividing throughout by 3, 18 divided by 3 is 6, so I get 6 times sec squared A, minus 3 divided by 3 is minus 1, so that's minus tan A, and minus 21 divided by 3 is minus 7. That's equal to 0. From previous trig identities, I notice that sec squared A is equal to 1 plus tan squared A, and I'm going to use that to simplify the problem in this case. So changing the sec squared A with the 1 plus tan squared A, I get 6 times that bracket, take away my tan A, take away my 7 equals to 0. If I expand the bracket, I get 6 times 1 is 6, plus 6 times the tan squared A, so that's plus 6 tan squared A, take away tan of A, take away 7 equals to 0. And again, just tidying up my numerical values, 6 take away 7 gives me the negative 1. So I end up with a quadratic now in tan of A. You can solve this with the equation if you want to. I've shown it solved here using factorization. So 2 times the tan of A minus 1 in the bracket multiplied by 3 times tan of A plus 1 in the bracket equals to 0. I've factorized the equation. To solve, I need to equate each bracket to 0 in turn. So 2 times the tan of A minus 1 is equal to 0. Rearranging, I add 1 to both sides and divide by 2. So therefore the tan of A is equal to half, or 0.5. And the second solution, I equate 3 times the tan of A plus 1 equals to 0. Again, taking away 1, dividing by 3. Tan of A is equal to minus 1/3, minus 0.3 recurring. So I've got my two ratios here of positive 0.5 and negative 1/3. Again, thinking back to our Astc diagram, we know the tangent curve is positive in the first and the third quadrant, and it's negative in the second and the fourth quadrant. Question 1D continued here. We're now going to find the values of A associated with the ratios we found on the previous slide. For the ratio of 0.5, tan to the minus 1 gives us the 26.56 angle, so A is 26.56 degrees, and that's a valid angle for the function here, because in the first quadrant, don't forget, all waveforms are positive. Don't forget that tangent is also positive in the third quadrant here on our Astc diagram, so a second solution will be 180 degrees plus the 26.56 to give us 206.6 degrees. That's our second solution. So in the first and the third quadrant, that positive ratio is relevant. Looking at the second ratio we found, the minus 1/3 here, tan to the minus 1 of minus 1/3 is minus 18.43. So a negative ratio occurs in the second quadrant and in the fourth quadrant. So if you take the fourth quadrant here, A will be 360 take away 18.43 degrees. So to get this value here, it's 360 take away 18.4. So 341.57 degrees. and to find the final value of A, it will be in this quadrant, and that will be 180 take away the 18.4 degrees. So the final value of A is going to be 161.57 degrees. So in the second and the fourth quadrant, that's where the negative tan ratios occur. So our solutions for A are in degrees and minutes I've used here, 26 degrees and 34 minutes, 161 degrees and 34 minutes, 206 degrees and 34 minutes, or 341 degrees and 34 minutes. Don't forget, degrees, minutes and seconds is a button push on your calculator. Question 1D continued here, just showing you the plot of the tangent curve and the ratios we've got and how the solutions occur here. I'll let you look at this and try and follow this in relation to the previous Astc diagram. Okay, question 2D, this is a type 4 solution. We're asked to solve 3 times cosec squared theta is equal to 4 times cot theta plus 5, within the range of 0 to 360 degrees. So the first thing I need to do is rearrange the equation to get all the terms onto one side so it equates to 0. So in this case I'm going to take 5 from both sides, and I'm going to take 4 cot theta from both sides. So I end up with 3 cosec squared theta minus 5 minus 4 cot theta is equal to 0. Using my trig identities from previous work here, I notice that cosec squared theta is actually equal to 1 plus cot squared theta. I'm going to use that relationship here. If I replace the cosec squared theta with the 1 plus cot squared theta in brackets here and expand the brackets, I'll be able to simplify my equation. So expanding the brackets, I get 3 times 1 is 3, plus 3 times the cot squared theta is 3 cot squared theta, minus the 5 minus the 4 cot theta is equal to 0. Bringing the numerical values together, I've got 3 take away 5 gives me minus 2. So my equation is 3 times cot squared theta minus 4 cot theta take away 2 is equal to 0. I've now got a quadratic equation in terms of cot theta. Note in this particular equation it does not factorize, so you'll have to use the quadratic equation. This is shown on the next slide. Okay, question 2D continued here, just repeated the equation for convenience. So 3 times cot squared theta minus 4 cot theta minus 2 is equal to 0. I'm going to solve this with the quadratic formula. So cot theta is equal to the minus b plus or minus the square root of b squared minus 4ac all over 2a, our standard formula. Don't forget that the a in this case will be plus 3, the b will be minus 4, and the c will be minus 2. I will let you go through the process of doing the quadratic formula. What you should end up with is cot theta is equal to 1.721, or cot theta is equal to minus 0.3874. So those are our two ratios we need to consider. Question 2D continued here. Okay, now we've got the ratios calculated on the previous slide. We're now going to find the angles associated with them. So taking the ratio of 1.721 on the previous slide, I need to find the arc cot, or the cot to the minus 1, of 1.721. But I'm not going to solve it in terms of cot, I'm going to solve it in terms of tan. Don't forget that cot is actually 1 upon tan. So I could actually have arc tan, or tan to the minus 1, of 1 divided by the 1.721. So using that relationship, that reciprocal relationship, I can write the arc cot of 1.721 as the arc tan of 1 divided by 1.721. Just take a moment to think that through to yourself. Typing on my calculator, the arc tan, or the tan to the minus 1 of 0.581, which is a decimal, gives us 30.16 degrees. So that's the solution for theta, because in the first quadrant the functions, all functions are positive, so 30.16 is a valid solution. And don't forget, we're talking about a tan function now, so the tan function is also positive in the third quadrant here. Okay, so we're going to get a solution that's 180 degrees plus 30.16 degrees from the horizontal. So my second solution for theta, 180 degrees plus the 30.16. So 210.16 degrees is my second solution related to the positive 1.721 ratio. Taking my second ratio from the previous slide, that was negative 0.3871, so I need to find the arc cot, or the cot to the minus 1 of that. Again, I'm going to use a tangent function, so I'm going to find the tan to the minus 1 of minus 1 over 0.3874. So that's arc tan of, using the calculation there, of 2.5813, which gives me a negative 68.82 degrees. So thinking back to our Astc diagram, in the second and the fourth quadrants, the ratio for tangent is negative, so those angles relate to those quadrants. So having that minus 68.8 degrees from 180 degrees will give me another solution. So theta is 180 take away 68.82 degrees, so 111.18 degrees is another solution I've got here. And the final solution will be 360 degrees take away the 68.82. That's in the fourth quadrant, and that will give me 291.18 degrees as my final solution. So my final values for the angles theta in this case, and I'm using degrees in minutes here, 30 degrees in 10 minutes, 111 degrees in 11 minutes, 210 degrees in 10 minutes, and 291 degrees in 11 minutes. Don't forget the degrees, minutes and seconds is the button push on your calculator. For your reference, a bibliography use, some very good texts here I would suggest you refer to for further information. I hope you found this presentation of interest and helpful to you. Thank you for viewing.